And hello, welcome YouTube. The last video we talked about how the Jacobians and everything were constructed. Where would you usually find these things? And yeah, there's still a lot of documentation and stuff to go through, but yeah, we'll start somewhere simple today. Just want to talk about how to actually use those matrices so that the language, the syntax of SpiceSharp and the classes and everything becomes a little bit more familiar. Okay, so where do we usually take a look for? Oh, there's the view PDF button. Yes, where do we take a look for the matrix solvers? Okay, the matrix solvers are found under well, SpiceSharp 3 master, SpiceSharp algebra. I don't know if I said it in the right order, but it's under the algebra folder. Okay, solvers are usually found here. Okay, and solvers, they will actually contain a matrix and a right hand side vector, just like what we have for this. We have a matrix here. Okay, we have a matrix here. Okay, we have a matrix here. Let's see which one is. Yeah, I guess I'll just use that matrix example. Okay, we have a matrix here. This matrix here. Yeah, I think I should paste it a little bit, make it a bit more explicit. But anyway, we have the Y matrix here and the right hand side vector. Okay, though this isn't really the full thing. Let's make it a little bit more explicit, like over here. Okay, so where is this? Yeah, this is the matrix I want to show. Okay, I'll put this here, and I'll just say note we are solving for, and then I'll put this big matrix thing over here, but of course I have to make a few additions to it. Okay, yeah, so we have this Jacobian matrix. We need to separate out this x1, delta x2, delta x3. Okay, so this in a 3x3 matrix case. Okay, we are solving for something like this. Okay, just to really make it clear, I want to have x1, x2 and x3 at the k plus 1 iteration. So I'll just put k plus 1 like that across all of these things. Okay, so the k plus 1 iteration is like that. Okay, so I will have to change it, of course. I have to do something like this, because this is what delta x truly is. Okay, okay, this is what delta x truly is in substitution. So this, the k plus 1 refers to the iteration of the k plus 1th iteration. I'll probably put some brackets over it just to make sure it's a little neater. So this is the example for 3x3 matrix. Okay, in the real case, of course, we will have many more equations depending on how large and complex our system is, but it's easy to visualize a 3x3 matrix. Okay, that's like a minimum, so to speak. Okay, 3x3 or 4x4. Okay, so you just do 3x3 because it's very easy to visualize. Okay, so I'll just remove rewrite this as. Okay, I'm going to just refactor. Not refactor, that's not the right word. Okay, so I'm going to move this x1, x2 and x3 matrix over to the right hand side so that we have the full right hand side matrix. Okay, so I'll just copy and paste this. Okay, and then I'll just have a plus here like that, and I'll remove the minus signs from the left hand side. So 1, 2, and 3. Here we go. Okay, undefined control sequence for \x. Okay, fine. Oh right, I forgot. I also need to put in this Jacobian matrix here. So let's just put the Jacobian matrix in front. So I'll put this here so that the LaTeX doesn't go too long. Oh, misaligned. Let's see whether this thing compiles properly first. Okay, so this thing over here needs the matrix on the left, so I will just put that. Let's see whether it's aligned properly. Oh, right, okay. So I need to do a begin. Okay. Just need to watch how I copy and paste, but essentially, the right hand side matrix is all these things on the right. Of course, all the Jacobian. Note that the Y matrix or Jacobian will be evaluated at. Okay, we're going to do text BF. Now do inline equation here. I'll do a vec or override arrow. X to the K. Okay, so it will be evaluated. Okay, the Jacobian here, all these partial derivatives will be evaluated at the where is it over left? Over right. Okay. It will be evaluated at this and the xk iteration. You see this vector here? This vector over here. Okay. All these values will be substituted into this Jacobian matrix here, because these partial derivatives are functions of x1, x2, and x3. So you need to back substitute in x1, x2, and x3. Okay. At that particular iteration, and that will be like a constant or a matrix of constants. Okay, so we substitute this all the partial derivatives in the Jacobian with the x values at the current iteration, and these all become constants for that iteration. Okay, so all of these will just become numbers and not as scary. And then F1, F2, F3 we'll need to substitute everything in as well at x or x of k, and then pretty much we will have this solution right here, x1, x2, and x3 at k plus 1 iteration. Okay, so this whole thing here is sort of the right hand side vector, and we can extend it. And I won't talk about it anymore. I probably think you're quite familiar. I hope you are. Okay, so let's just go through. Okay, I've written down where to look so that you don't have to go into the rabbit hole. Alright, so this has found under this here. So once we have our Jacobians, the matrix solver takes care of the rest. Okay, the inversion of the Jacobian, matrix multiplication are taken care of it by these solvers. So usually what this solver does is that, yeah, you need to, of course, condense it yourself. All of these things on the right hand side, you need to condense it into a right hand side vector. The things on the left hand side will be decomposed. I think most of the time they like to use the LU decomposition, lower upper decomposition, so that it's easier it's faster, computationally faster than doing like a reverse row echelon or whatever thing. Okay, so it will be decomposed into LU, which is very good for large matrices. And after that, you have a LU decomposition, and then you just solve from there. You multiply instead of finding the inverse of this whole thing, you just find the inverse of the lower or upper matrix. I think you find the inverse of the lower matrix, and then you just multiply throughout, and then you back substitute. Okay, that's assuming you know what LU decomposition is. Okay, so I'm just wondering, should I just explain LU here? But okay, just know that it's a solving algorithm for now. I hope you are familiar. Okay, so next step is that how then do we find the how do we define the matrix and then tell the solver to solve it? Okay, so there is a very good place you can take a look. Okay, there's a good way you can see examples. Okay, for example, this SparseSolverTest.cs is under SpiceSharp tests. Okay, SpiceSharp tests, algebra. Then you go under here for sparse matrix tests. Okay, so this thing actually has a link. You can actually click on it if you open the thing with a let's see. I'll go to theory, and then I'll open the file explorer here. So you see, if I just open a PDF here, okay, you can actually click on the PDF, and then there'll be links for you. You can just click it over here. Okay, but over here in my PDF thing, the opening URL is disabled in the settings. You can of course open with Firefox and just click on this. It will immediately bring you to the relevant links. So it's pretty nice when you have the URL in LaTeX. Okay, so let's take a look. Line 43 to 72 of this sparse test solver. So I'm going to click this link. I'm going to cut this. I want it in dark theme. Dark theme is always nicer for me. So SparseSolverTests.cs. Let's take a look at line 43. Okay, and we'll take a look at how solvers actually are supposed to be programmed. Look at line 43 to 72 or 43 to 72. Here, how do we usually do a sparse solver? Okay, over here in C#, we are this is actually an N unit test. I like to use X unit, but our friend here likes to use N unit. So this is pretty much just a script, a code that is being run. Okay, so all the code that's being run inside the test is under this public void blah blah blah. Alright, so how do you start the code? Okay, the SparseRealSolver is a class which we instantiate an object called solver over here. Okay, so SparseRealSolver is the class. You can go and take a look at what's inside the class later on. But how do you use it? Okay, here are some more complex users of this solver, so just ignore this part first. But you can see very clearly, okay, that there is a matrix being constructed here. The matrix in this case is an array of doubles. Okay, it's an array of doubles, so that there are some arrays, documentation you can read up of arrays. So these arrays will actually implement lists and enumerables. So if you're familiar with that, I hope you are. So this essentially does that. So yeah, so the nice thing is that in C# arrays are actually objects, so they're much nicer to work with compared to C++. So they work a bit like arrays in Python, in the sense that arrays are also objects in Python. Okay, but anyway, here is an array of matrix. So there's an array of doubles. Okay, an array of doubles. So the double array is a matrix. So we are declaring a double, and then we are setting the value to be equals to this whole thing right here. So you can see that this really looks like a matrix already. Okay, it's a 4x4 matrix, as you can see. So that 4x4 matrix is essentially what we have on this side. Okay, once we actually substitute in the xk vector, okay, x1, x2 and x3 at the kth iteration, okay, once we do that, that will be a constant. It will just be a string of numbers in a matrix, and then yeah, we can actually plot them out here. The right hand side vector, which is everything else on the right hand side that's not multiplied into x1, x2 and x3 at k plus 1, this will all be on the right hand side, and this will be the right hand side vector that you see here. Okay, how do you then put both of these arrays into the solver? Okay, the solver itself will have a matrix object and a right hand side vector object. Okay, can you see here? Okay, solver.GetElement matrix location. So we'll need to take a look at, for example, the SparseRealSolver. We'll see what's actually inside. Okay, SparseRealSolver. Okay, SparseRealSolver. Okay, where is everything? Where's the IMatrix, for example? Okay, you will not find it here because these properties here, or these properties and methods here, these are actually just additional methods that are specific to the RealSolver. Okay, you can take a look. SparseRealSolver actually inherits from SparseLUSolver. So let's look for SparseLUsolver.cs. Okay, SparseLUsolver actually inherits from PivotingSolver and implements iSparseVector, iSparsePivotingSolver, and iParameterized Markowitz, whatever that is. Okay. So there are lots of things over here, so I will not go into it, but we are looking for IMatrix. Okay, again, this one doesn't have an IMatrix in it, but this thing, we can see it actually inherits from PivotingSolver. So there are pretty lots of levels of inheritance, which is good if you want a tightly coupled thing. Okay, tightly coupled class set. And for this one, it kind of actually makes sense. You do not want to do so much dependency injection, but I digress. Okay, so let's just look at where the PivotingSolver is. Okay, so PivotingSolver is the class that you see here. You'll see public abstract partial class. Now, what do these keywords mean? Public, you should know. It's pretty straightforward. It means that all the members in the class, unless you specify otherwise, I mean, this class should be accessible to the public. You can instantiate objects from it. Okay, abstract means that, okay, it means that you have, this class is not meant to be used on its own. Okay, it needs to be inherited by some other class. Okay, abstract classes, C#. Okay, so use the abstract modifier to the thing that's modified to indicate that it has a missing or incomplete implementation. So not all the methods here are complete, so it's kind of just there to house a lot of things. What things is this thing housing? As you can see, there is a M. Okay, this is a matrix here. You see, this is it actually stores a matrix. Okay, protected M matrix. This is actually a matrix right here, and you will also see a vector right here. So this actually gets the reordered matrix and vectors. Okay. Yes. And there should be a GetElement as well. Or maybe that's actually done over here. GetElement. Okay, see? This is the GetElement method, which is actually used right here. Solver.GetElement. Okay, solver.GetElement. Okay, a matrix location is actually specified for this one in a nested for loop right here. So just pay attention to this part first. Solver.GetElement. You actually have to supply a matrix location. So this is the GetElement with the matrix location as an input. Okay, location equals to blah blah blah, external to internal location. var alt equals matrix dot get element. Okay, so what is this thing doing is getting the elements of the matrix. Okay, he's getting the elements of the matrix. Where is the matrix? The matrix is right here. This is the reordered system matrix thing. Okay, so this is a property. the reordered matrix. So you can search it here. Matrix is over here. Okay, sparse matrix. Okay, so yeah, there are lots of intermediate steps, but the important one for us is to look at this GetElement. Okay, var else equals to matrix.getElement. Okay, basically you're getting elements in the matrix. What is this element right here? Okay, what is this element? Okay, elements are actually literally the elements within the matrix. Each of these actually has a class. Okay, if you take a look, okay, when you see this thing called here element.cs actually this is a class representing all the properties, all the things that you can do with actual elements in the matrix. So that's why there is this element.cs. It's applicable for both matrix and vectors. So you will see this being inherited by both of them, or somehow yeah, dependent on both of them. That's what this element T is about. Okay, so there's something about degeneracy here, which, if I'm not wrong, okay, never mind, I'll just skip this part. Okay, so the element get matrix, what this class does is just to return the element at the particular matrix location. Okay, that's basically what this thing does. Okay, that's basically what this thing does right here. So I won't go into too much detail how it works, because we just want to know how to use this thing. We don't exactly need to go into the nitty-gritty, because we don't want to reinvent the wheel. And I mean, roughly, as you can see here, this is what we do. Okay, so to set the matrix in there, you can see that if the matrix, okay, this matrix at the specified row and column index, if it doesn't equal to 0, okay, that's what this exclamation mark is here is for. Okay, solver.getElement at this new matrix location. So this whole getElement method actually returns you an element, okay, a matrix element at the r+1 c+1. Okay, so this actually tells you the matrix location at the row and column. Okay, though over here the row actually starts from 0, whereas the row here actually starts from 1. So there's a different numbering convention. That's why there's a +1 here. Just from looking at this, that's my guess. So this matrix location is at the rows +1 c+1. That is where the actual matrix location is. Okay, we get the value of it, and then after that we set it to the matrix value. Okay, this matrix value at whatever row and whatever column. Okay, whatever row and whatever column. So does the matrix actually look like this in this order, or is it flipped? Well, we can take a look at that later. But this is what this line of code is doing. So it's for all the rows and for all the columns. All right, for all the rows and all the columns, what we are doing is that okay, for all the rows. Okay, so it looks like this is for the columns. So when we, yeah, for all the rows and all the columns, we actually get the elements of that specific row and column, and then we set the value of the element to whatever row and column is in our specified matrix here. So this is what this nested for loop is doing, and that's only one part. Okay, that's only one part. The second part, wait, hold on, need some water. Okay, second part. Second part is that you can see that this you are also setting the right hand side vector right here. Solver.getElement r+1.value equals to RHS r. So where can we see that? Okay, again, similar to the element part, we also see that the getElement has another overload. Okay, overloads means to say that depending on the type of inputs you give to the function or the method, the function will then behave differently. So if you supply a matrix location for this getElement, you will actually be getting the element, okay, the element, one of these elements inside the matrix, with a specific row and column. If you just apply a row, that means you are changing the vector which is inside the solver class. Okay. So again, the pivoting solver, how the class works, how solvers work. Okay, the pivoting solver here actually contains a matrix and a vector. Okay, there's a matrix and vector here, and these matrix and vector are stored as properties. These are stored as properties inside this what do you call that? They are stored as properties inside the they are stored as properties inside this partial abstract class. So this class is abstract because it must be inherited elsewhere. Partial means that this is only one part of the class file. Means that there are other parts to this file, and it's just split up so that each line of code doesn't actually stretch too long. Okay, this is actually like 200 lines of code, which is good if you want to read short lines of code. It's easy to edit, it's nicely segmented, so that it's more easily managed as compared to you have a big file with 5,000 lines of code. Very hard to see where errors are like that. Okay, so that's the pivoting solver. Okay, so here we go through. We actually go through how to actually implement, or rather put in matrices. Okay, the matrix and the right hand side vector, we actually can put it into the solver by actually using a for loop. Okay, we use a for loop here to specify the elements one at a time. Okay, we specify the elements one at a time using a for loop. Okay, so this is a nested for loop that does it for the matrix. This is the for loop that does it for the vector. Okay, so once this is done, you have already put in the data into the matrix. Yeah, you have already put in the data for the matrix thing. Okay, you put in the data for matrix and right hand side vector, the Y matrix and the right hand side vector for this solver. So the solver, you have to specify the right hand side vector and matrix, right hand side vector and matrix. Yes, that's correct. And then after that, you do what you need to do. For example, in this case, you actually get the solver size out, and you actually run solver order and factor. Okay, solver order and factor will actually do some ordering on this, and it actually returns the size of the matrix. Okay, the size of this solver. What's the size of the solver? The size of the solver, if you took a deeper look into the documentation, is actually how many equations there are. So I actually wrote them down. Okay, I wrote it down a little bit more here. So you see, setting matrices within an RHS vector values within a solver. So this is more or less my notes, which I'm going to give it up. Okay, putting on GitHub, of course. Getting number of equations within the solver. Okay. Oh yeah, you can click the links and you can take a look in your own time. Right. So getting number of equations, we actually use the size attribute. Okay, the solver size actually represents the number of equations represented by the matrix, or this system of equation, the matrix and the right hand side vector. Okay, so that's what it does for you. Okay, and then order and factor also does something similar. It returns you how many independent equations there are, because this is supposed to so-called help you get rid of all the redundant equations that are linearly dependent. Okay, but if I'm not wrong, that's its function. But the return type of order and factor, okay, order and factor is actually done in IPivotingSolver and SparseLUSolver. This is where it is. So the order is equals to size minus degeneracy. Degeneracy is how many linearly dependent equations there are. And then order is actually returned over here. Order is actually returned here. Then yeah, it says that if matrix is factored before, reordering is not required. Okay, there is some there is some pivoting process or whatever that's going on. I'm not really sure, but that's not the focus of this video. Focus of this video is how we can use these solvers and what do each of these methods and properties actually do. How does it make sense? Okay, so the other part that is good if you want to see how these matrices are solved, okay, the matrices are solved in, I think, towards the end. Okay, so this is line 174 all the way to 210, which apparently I have not written down here yet. Okay, so let's see. Let me write a subsection for solving. Subsection solving the matrix system of equations with the Ymatrix and RHS vector. Okay, so this is line C, line 174 of, and I'll give you this URL here. Okay, see lines 174 all the way up to 199. So look at 174 or 174 to 199 of this URL right here. We'll see that specifically within this okay, 174 not to 199, you have to go all the way to 234. My bad. 234. Okay, and what do you do? Okay, notice the last part. After we actually set up our matrix, they are doing what? Get element things, assert equal, solver size, solver order and factor. Okay, this is the new bits, 255 all the way up to 234. Okay, they actually declared a new solution vector. Okay, this solution is a new dense vector. Dense vectors are just vectors that have most of its elements like not zero. Okay, so when you find a dense vector class, dense vector classes are actually defined here. Okay, dense vector actually is just a class that implements IVector. Okay, IVector is a vector interface. Okay, so this is just a class that represents a column vector. Okay, it's nothing more than that. Okay, var solution equals to new dense vector, and this dense vector happens to have some complex numbers in there, real and imaginary numbers. Okay, and it will be so this is a constructor that is being run. You're declaring a new instance of the class, then a constructor will be run. So you need to supply a solver size to this dense vector. Okay, and the solver of course needs to solve for a solution. Okay, so this solution vector is kind of empty. It's an empty vector that has that you only feed in the size of this vector. Then you feed in this solution vector into the solver.Solve method. Okay, and this specific solver is a sparse complex solver right here. Sparse complex solver, no longer SparseRealSolver. Okay, sparse complex solver. Okay, and okay, again the same things are happening here. You actually notice that in this nested for loop, you will actually define the elements of the Y matrix one by one using the for loop. And over here, you actually read off this right hand side vector. Over here, you do it one by one also. Over here, you actually reset some of these elements to 0. Okay, add some 0 elements as what this thing actually says. Okay, and this is a 7 by 7 matrix. Okay, and a 7 row 1 column vector. Okay, so this is what this part is doing. Okay, so there's the solver.Solve thing that's being run. Okay, the solve method is actually a void method. Okay, the solve method is actually a void method that actually takes in a vector, that anything that implements the IVector interface. Okay, it takes this in, and then you see it does this bunch of code here. All of this substitution, forward substitution, backward substitution. So this is probably LU decomposition, just by the looks of it. And then this unscramble method is run Okay, unscramble method is actually defined right here in solver translation.cs. Okay, void unscramble. Okay, and then this bit of code here is actually done to the target. Okay, target, IVector target. So that's the gist of what solvers do. You feed in an empty solution vector. Feed in an empty, where is this? Oh, wrong code. Yeah, feed in an empty solution vector. As you can see here, empty solution vector, and the solver.Solve will take care of the rest. Okay, once this solution is fed in, I don't know why it has no return over here. It'll be nice if they actually do a return. Okay, a return type. Okay, so yeah, I don't know whether this return. Okay, there's no return type here. Okay, there's only an input. There's not really an output. Okay, no output here. Okay, so the methods for solving and manipulating the matrix are within the solver solver object, which is in this case an instance of a sparse complex solver in this line of code. Okay, next thing you do is to just run the solve equation, and then okay, this is the unit test part where we assert whether the reference is equal to the the reference is equal to the value of the solution. So you see that the solution here is just fed into the solver, and then from the looks of this code, the solver should have actually given this solution thing a new value. That's why you're actually asserting the reference real to the solution right here. Okay, the solution.real over here, and then there's some error tolerance here. Okay, so what this bits of code does, what the solver code does is just to alter the values of the solution right here, and then after that is supposed to you're supposed to be able to check it. I don't really know how that works because I am not really familiar with using void methods to change the values of something outside the class. Okay, I'm not that familiar, but apparently this is how it works in this test. Okay, alright, so that's how pretty much you use these solvers from the looks of this test. Okay, you actually define a matrix whether it's real or complex first. You set the matrix and right hand side vector property within the solver, one element at a time using a for loop, as you can see here and over here. Okay, of course you can set and access individual elements of the matrix one by one. Okay, after that, what you usually do is to create a vector, which is the solution vector. The solution vector will be it will just be this vector here, x1, x2, x3 at k plus 1. This is a vector and it's a solution vector. Okay, you make one that is perfectly the size of the solver. You feed it into the solver, and then solver.Solve will do everything for you. Okay, so this is basically how the solvers are run in SpiceSharp. At least the matrix solvers are run in SpiceSharp. There'll be a square matrix, there'll be a y vector, you define it, and then you do some reordering, pivoting, I don't know what. Okay, there's an order and factor step as well. And then after the order and factor step, then you kind of solve it. Okay, so this part is actually pretty important. You do the order and factor step, and then you solve it. Okay, and what this test is actually doing is to compare the results of this solver.Solve method to a reference over here, which I assume from this test name. Okay, from this test name, you're actually using MATLAB to was actually using MATLAB to generate this reference. Okay, so this is how you pretty much deal with it, solving the system of equations. So let's just one more time. I'm getting really naggy, but itemize. Oh, begin itemize. Item So the first item is what? Define RHS and Y vector using for loops. Number two, order and factor. Item number three, create a new solution vector. Number four, feed solution vector into solver.Solve method. And number five, check the solution vector. Okay, at least from the unit test, this is actually what is going on. And I think I shall stop here. I will not go too much into detail, but definitely we'll want, since we know how to work it, definitely we'll want to try some very simple matrices to see whether this kind of thing actually works. Hopefully. Okay, so I think that's enough. I'll see you next time. Bye bye.